Okay, so what you're going to look at is some more related rates problems. You should have this worksheet for some notes and some practice problems. The first thing that you notice on the worksheet is that I gave you kind of some steps to solve, draw a picture, um, make a list of known and unknown, relate the variables, that means come up with an equation or a formula, take the derivative. So step 4 is take the derivative. Step 5, substitute and solve. So we've done some of these. These are just some other examples. I'm just trying to give you as many examples as we can. Important, remember things that are non-constant, things that could change, you don't substitute them in until after you've taken the derivative. And we'll look at a couple of those. So let's start with this first example. Example 1 says the width of a rectangle is increasing at a rate of 2 centimeters per second, and its length is increasing at a rate of 3 centimeters per second. What is the rate? At what rate is the area of the rectangle increasing when its width is 4 centimeters and its length is 5? So we're looking for the rate of the area. That's our unknown. So if I follow my own little steps here, first thing is to draw a picture. Again, my pictures are not great. I would have my length and my width, and it doesn't really matter which one you put where. Second one, make a list of what you know. I know that my rectangle is increasing the width, so my dw dt is 2 centimeters per second. I know my length, so that'd be my dl dt is increasing at 3 centimeters per second. And then I want to know at what rate is the area, so I don't know dA dt, so that's what I'm looking for. And it says when its width is 4 centimeters and its length is 5 centimeters. So those are not constant. Those could be anything. So hopefully you drew smaller than I did because I kind of made a mess of this. So I did that. Relate the variables in an equation. Well, area of a rectangle. Sorry about that. The area of a rectangle is length times width. So if I take the derivative, that'd be dA over dt. The rate of change of the area would be the width times dl dt. So the derivative of L times the width plus the length times the change or the rate of change of the width with respect to time. So product rule. So then our next step, or last step, is to substitute what we know. Well, we know the width is 4 and the rate of change of the length is 3 centimeters per second, plus we know the length is 5 and the rate of change of the width is 2. So we'd have 12 plus 10 is 22. So the change in the area with respect to time would be 22, and our label would be centimeters squared centimeters per second. All right, so let's look at another one here. This one, it says easy example. This one's actually a little bit harder, but we've done ones like this. Just think of like your walking problem that we did that first day. So it says a police car approaching a right-angled intersection from the north, so here's your police car, is chasing a speeding car that has turned the corner and is now moving east. So my speeding car is moving east. My police car is approaching this corner, so it's moving south. When the police car is 0.6 miles north of the intersection and the car is 0.8 miles to the east, the police determine with a radar gun that the distance between them and the car is increasing at 20 miles per hour. So I had to read that a couple times when I first did this. So they're talking about the distance between them and the car. They're actually talking about the hypotenuse distance. So they're talking about this. I called it c. So the rate of change of c is 20 miles per hour. If the police car is moving at 60 miles per hour at the instant of measurement, what is the speed of the car? So we know that the police car's rate, so you can call that whatever side you want. I called this side A and this side B. So we know that the police car, is moving at a rate of 60 miles per hour. We don't know how fast the speeding car is moving. That's what we're looking for. So I'm going to call that dA. And again, you can use any variable. We don't know that. So we have this situation. Now we got to figure out what formula or equation would relate A, B, and C. Well, hopefully we've done enough of these. This would be a Pythagorean. A squared plus B squared equals C squared. And we can take our derivative, which would be 2A times the derivative of A with respect to time. 2B times the rate of B is equal to 2C times the rate of change of C. And then we just have to plug some numbers in. Well, we know 2. Technically, do you see how all these have 2's? Let's just cancel those off. This is one less multiplication you have to do. We need A. We need to know the distance the car is from here. So we need from the origin. So how far is the car from the origin? It says the car, if I go back, the car is 0.8 miles. So A is 0.8. How fast is the car moving? We don't know. That's what we're looking for. Plus B. B would be how far the police car is moving, and that would be how far the police car is away, so that's 0.6. And now we need to talk about how fast the police car is moving. Well, the police car is moving 60 miles an hour, but remember, it's actually we're gonna put it as a negative 60 miles per hour because the police car is getting smaller, that side is getting smaller, equal, we don't know C, but we can find that in a minute. How fast is this distance, that hypotenuse changing? That's 20. So now we need to find C. So remember, it's a triangle. So if I had a triangle, so this is the if thing, this side is 0.8, this side is 0.6, and you did Pythagorean theorem, this side would just be 1.0 or 1, because it's A squared plus B squared equals C squared. So then what you have to do is you have to solve for dA dt. And I don't have a calculator with me, so I will solve for dA dt using my computer calculator, which might just take a second. So I'm going to pause. All right, when I do that, I get 70 miles per hour. So if you solve that, you get 70 miles per hour. Okay, so let's look at another example. This one is a little harder, and it says that there, but I think we'll be fine. So let's give it a try. A rocket lifts off at Kennedy Space Center in Florida. A camera is placed 2,000 feet away from the launch pad to film the rocket's ascent. The height of the rocket can be modeled using this equation, which is a quadratic equation, where S is in feet and T is in seconds. Find the rate of change of the angle of elevation of the camera at 10 seconds. So let's draw a picture. So I have a rocket over here, and I have a camera that is 2,000 feet away. That 2,000 is not going to change because it doesn't say it's going to change. So you have this camera over here. I'll put a little C there for the camera. It's filming this rocket going up. And so what we need to do is figure out what that would look like. Well, it talks about the angle of ascent, or the angle of elevation. So you're talking about a right triangle. You're talking about this angle right here. I'm sorry, my pictures are so bad. I'm trying to draw on the computer. It doesn't always work that well. So we are talking about figuring out, we have a rocket and we have this. So we have a vertical and we have a horizontal. We don't really care about the hypotenuse. So this is an angle, so we're talking SOHCAHTOA, so we're talking tangent. The tangent of theta equals some height, we don't know, over 2,000. So that is our formula. It says the height of the rocket can be modeled there. So this is kind of a special problem, so just keep that in mind. Find the rate of change of the angle of elevation. So we're looking for d theta dt. We're looking for an angle. of the camera at 10 seconds after liftoff. Okay, so let's take our derivative and then we'll figure out what we need from there. So the derivative of tangent is secant squared theta d theta dt. And we talked about this before. This is just going to be 1 over 2,000 times the derivative of h, which would be dh dt. Okay. Okay, so then we want to know at 10 seconds after liftoff, because we're going to need to know this side, the height side, in order to get my secant. So we need to know at 10 seconds after liftoff. So if you plug 10 seconds into this equation that they give you, that would give you the height of the rocket. So if I plug 10 in there, I would get 100 times 50. So you just get 100 from the t squared times 50, and that would give you 5,000. So the height of the rocket that we're looking at is 5,000. All right. So now we need secant. Remember, secant is just a fraction. It's a ratio. So secant is the reciprocal of cosine. And if you remember, cosine is hypotenuse or adjacent over hypotenuse. So that means the secant would just be the hypotenuse over the adjacent. So in order to get a number for secant, a fraction squared, we need the hypotenuse. So to do that, you're going to use Pythagorean's theorem to get that. So if I get that, that gives me 5385.16 is the hypotenuse. So what we're going to do then is you're going to have your secant is going to be this 5385 over the adjacent, which is 2,000. So you're going to have 5385.16 over 2,000. And you're going to end up squaring that times d theta dt equals 1 over 2,000 times how fast the height changed. So you have to go back and see, did they ever tell us how fast the height was changing? So you have to kind of think basic algebra. It's a little weird, but how fast did the height change? Well, at 0 seconds, it was at 0. And at 10 seconds, the rocket was at 5,000 feet. So the rate of change that here is actually 500 feet per second. So I'm going to multiply this by 500 feet per second. So now you're going to use your calculator and get what d theta is, and that will be in radians. So I'm going to hit pause again so I can get to my calculator. So if you did that, sorry, again, this is really messy. I got 1/30th radians per second. I think that's like 0.03 radians per second is what you should get. Again, that's a pretty tough problem. You're going to look at another rocket one later on that isn't as hard because this one you had to use some secondary formulas. Okay, the last problem here is just another cone one. I went through one in class on whenever we had the last class. So if you think you can do this one, that's fine. You don't have to watch the video, but it's just, I wanted to give you another idea of the cone problem. So again, remember we talked about a cone. The problem with the cone is it's too many variables. We have r squared and h, so we need to change this equation into something that's only two variables with the volume in either r or h. I'm going to go skip kind of my steps and go right to the question here. It says, how fast is the water level rising? So the water level is talking about h. That means I want to get rid of r. So I already have a picture there, so just remember I want to get rid of r. So I'm going to take this formula for the volume of a cone, and I'm going to rewrite it in terms of h. So in order to do that, I need to get rid of r. I need the relationship between r and h. So here's r and h. The radius of the cone is 5 and the height is 10. So you can see there that the relationship is that r is 1/2 of the height. or you can write it out as a proportion, however you want to do that. Okay, so I'm going to rewrite my actual just volume formula from geometry in terms of R. So it's going to be 1/3, or in terms of H, I'm sorry, 1/3 pi times 1/2 H squared times H. I'm going to skip a step because I'm really good with fractions, I guess. But this is pi H cubed over 12. That's my formula. Now I'm going to go back and actually read the problem. It says water runs into a conical tank at a rate of 9 cubic feet per minute. The tank stands point down and the height is 10 and the radius is 5. How fast is the water level rising when the water is 6 foot deep? That is a constant, but it's a changing constant, so you can't put that in until after you find a function in terms of rate. So to do that, take the derivative. The derivative of volume would just be the rate of the volume per time with respect to time. This expression we have over here would give me 3 pi h squared over 12 times the rate at which the height changes with respect to time. I'm going to simplify that one more time because you guys know I can't handle fractions like that. So it's pi h squared over 4 times the change in the height with respect to time. So going back up, they gave me the rate of the volume was 9 cubic feet per minute. So 9 is equal to pi times h squared, which h is, what is h? H is 6. So 6 squared over 4 times the rate at which the height is changing of that water. So we can solve that. It looks like it's going to work out nice because 9 times 4 is 36. 6 squared is 36. So I get 1 equals pi dh dt. And then so pi, 1 over pi feet per minute is the rate of change. Oh my goodness, is the rate of change of the height. And again, if you want to put that as a decimal, you can. It doesn't matter to me. I know in real life you wouldn't tell somebody 1 over pi feet per minute because they wouldn't know what you're talking about. So there's your examples. I would take a minute to look at this last little thing here and maybe just write down something that new that you've learned today or something that will help you remember how to do some of these problems. Again, there's another page to this. And I just want you to work on them. I'm going to write when they're actually due. These problems aren't due until the test day, but these are good practice problems for the test. All right.